Today I wanted to walk through some, and we can only cover some, of the hydrogen technology areas of interest. I want to try and relate some of that back to things that are happening in Tasmania, but more importantly, look at the pathway to implementation. We could talk about research forever and ever, but if we don't get the links right and work with the industry and bring things to practical use, then I think we're failing in following through. Research on its own needs industry, and industry needs research, but we need to get the timing and the partnerships right. So I'll quickly, for those who might know, a very quick introduction to CSIRO. We'll talk generally about decarbonisation of energy and industrial systems. Decarbonisation is really the flavour of the initiatives across all of these different areas, meaning reducing CO2 emissions ultimately. We're talking about hydrogen as an energy carrier, and that's what it is. It's a means of storing and carrying energy. It is not a fuel in its own right. We have to make it, we put energy in to make it, and we get some of that energy back when we use it in whatever application it may be. So it's not a fuel, it's an energy carrier and storer. I want to talk some of the key enabling technologies. What technologies might we need to join the links between the source of hydrogen, how we make it, and how do we get it into practical systems? And given the diversity of the industries and the complexity of the businesses around them, that is not a straightforward process to stay in business and transition necessarily to hydrogen as your energy carrier. And I want to use that as a bit of a step to say, what might we need to do to start to scale and apply some of these technologies and lose the mindset that we have to do a massive step change, but how do we work with the existing industries at scale and gradually transition effectively so we can end up with the types of energy scale and supply that we have today, because we can't go back and start from cottage industry again and rebuild what is the equivalent of the world oil and gas and coal industries overnight. The CSIRO it has about 5,500 staff at the moment. It goes up and down. It's Australia's national science agency, so it's a government agency, it's not a government department. We have labs, about 55, maybe 56 places around the country at the moment, run through 9 sort of major sort of discipline or sector-based business units. Budget of the order of about 1.2, 1.3 billion, of which about 600 million or so comes from the federal government, up and down. But 40 to 50% of our research projects largely, on average, are externally funded. So what are we doing? I think I've covered some of this. To transition to net zero, as we call it, that is net zero carbon emissions from the life cycle or the value chain in a timely way, it needs to be doable. It needs to be affordable and competitive, or we won't do it. It needs to end up with a secure and reliable energy source. It's all very well to put in a country full of solar panels, but then find that we can't operate at night. And it needs to be clean and sustainable, so we need to address our primary issue of emissions reduction, but still be able to maintain the lifestyles and the industries that we need. And the attention to date has largely been on the electricity sector, and perhaps rightfully so. For more than 30 years that I've been working in coal with those technologies, it was all about reducing the emissions for power generation. The solar cell expansion has been about electricity generation, mostly feeding into the electricity sector directly, and that 34% covers both industrial and domestic use of our electricity sector. So that's where most of the focus has been, on decarbonising emissions with CO2 capture, high efficiency power cycles, gasification combined cycle, natural gas combined cycle, etc. That's been the biggest interest. Now the other 3/4 or 2/3 are more difficult to abate in that they're not so centrally focused as emissions, and they're dispersed across more complex industries, be they high temperature metallurgical processes, agricultural processes, manufacturing, chemicals, etc. So we have to do all of those, and what we're finding is those industries now more and more needing to work together, because we're talking about a common energy carrier now, a chemical energy carrier in hydrogen. And that's common with many of those sectors. Now, to do that renewably, at least Australia has the opportunity, or it has the resource of renewable energy. We have some of the highest solar installation in the world across Australia. So it's one of the red ones, and we're nearly all red, so we're in a better position than many. We have potential for up to 25,000 gigawatts of installed solar potential, but that would mean giving up a lot of other things. We need to be able to find out how to use that and how much of that we can use. This hydrogen strategy, the National Hydrogen Strategy, was sort of published in 2019 through Alan Finkel, the Australian Chief Scientist's Office, and that has a number of scenarios and trajectories, and that was sort of looking at global hydrogen demand increasing, because other countries have got to do exactly what we're doing, of up to something like 9 million tonnes per annum by 2030. I think that'll be easy, Matt, but enormous by 2050 to reach those decarbonisation targets. 230 million tonnes. That is, it doesn't sound like a lot of steel, but it's a heck of a lot of hydrogen, which is one of the lightest chemicals on Earth. So our work is around how do we bring those systems together? How do we optimise the renewables? How do we make sure those technologies not only are efficient in the way they work, but in the resources they use, in the way they can be recycled, in the way they can be operated? And how do we bring them all together? We can't just rely on one. You know, we see a lot in the media of, is it this or is it this? Oh, that was the wrong button to push. Is it one or the other? It's not. It's all of the above, and it needs to be all of the above, because, as I said at the beginning, ultimately, to meet those net zero, we've got to replace or change or transition the equivalent of the entire world's oil, gas, steel manufacturing industry. It's too big to take just one path and take that as a silver bullet. So a lot of our work is on helping integrate what's there with the appropriate industry, look at it holistically. Just because one chemical is easy to make doesn't mean it should go to every application, because some industries will have a choice and some will not. And globally we need to optimise the distribution of those resources. Hybrid systems, utilising different technologies coming together, will be very important. And the key enabler is, how do we reduce the risk of making the transition and create those connections between industry sectors, which today don't really talk to each other, they don't work with each other, but their technologies are well known and mature within their sector. How do we bring them together effectively to achieve both the energy and the decarbonisation? So we've been doing a lot of work now, initiating in the coal industry on CO2 capture. Coal industry is a power generation, an ideal place to begin that technology. We now need to adapt and roll it out into all of the others which have less concentrated and more dispersed CO2. Starting to look at how might we use CO2 for those industries that must have hydrocarbon fuels, and there's at least one, the aviation sector, will rely on hydrocarbon fuels for quite a long time. So how do we use CO2 where we need to? And how do we reduce the amount of energy where possible through recycling some of the resources we already have? A lot of energy spent in mining, processing, preparing materials for batteries, etc., and solar panels. And how do we start to bring those things to a longer life so we not have spending more and more and more on what is really a difficult to harness resource? Managing our waste. You know, landfill is probably not the most energy efficient way for us to utilise what effectively are hydrocarbon resources and hydrogen resources for some of these things. So that's the researchy side. What we've tried to do in CSIRO is set up what they call a number of missions which try and pull together the research, the industry, nationally and internationally, to help support a bit of cohesion between sectors. So the mission is recently set up, bringing together what we call a knowledge centre, so try and get a database of what's going on, who's doing what are the industry projects, where might there be linkages, and how do we provide some sort of online tools or tools that will work across those sectors to help those industries with life cycle analysis, etc. We're doing feasibility studies and what you call roadmap type studies to help show where those industries might come together. trying where we can to support proper industrial demonstration projects with relevant research, which either helps enable them now or provides the confidence for them to move forward with technology improvements down the track. And in the bottom right there, enabling science and technology, that's our core business. The technologies that need to be tweaked, that need to be developed or improved, that can be available within any number of businesses. And we've got quite a lot of invested stakeholders, and of course naturally through the government and arena and things, very broad reach into community applications. One of the things that's part of the Knowledge Centre is in fact that social licence aspect. All of these industries, they have their impacts, they mean big change, and we've got to work as a community to make sure, as I said earlier, use the right things in the right place and manage the balance about why we set out to do this, to be sustainable in the first place. If we lose all our farms because they all become solar fields, then that's not really sustainable in a holistic way. So the social aspect's really important. So let's move to hydrogen. Just accept for a moment that it's a nice energy storage mechanism. We'll come back to see why that is. And it sounds really simple. We just make it. We can use solar radiation, solar PV panels. We can make electricity, electrolyse water and make hydrogen. Sounds really simple. There are other pathways, but we just got to make it. And you often hear the proponents of big projects, we'll just make hydrogen and then we'll convert it into something and we'll ship it to the market. We've got to move it, we've got to store it. Now, that sounds simple too. It's not. Hydrogen is very difficult to move around. As I said, it's very light, very low volume, very low energy density. We've got to address that. And we've got to find ways of using it at the other end, getting it back into a form, if we've changed it, where it's useful, and getting it into different industries and applications than where we used to have fossil fuels. Now, think globally here, we've got lots of renewable energy that we can do some of these steps with. Many countries don't. That's why we export coal, and that's why we export gas now to places that don't have many resources at all. So this looks complicated. It is more complicated than make it, move it, use it, but it's basically what's shown on this diagram. On the left-hand side, we're looking at hydrogen as a mechanism of storing renewable energy. That's the primary initial goal. Be that hydro, well that's not, what have I done wrong? Be that hydro, like we've got in Tasmania, be that solar, wind, even solar thermal technologies, that we're doing a lot of work there. How do we store that energy in a form that can either be used later or stored for a long time, or that can be transferred somewhere else? So things like, photovoltaics, wind, etc., through electrolysis to produce hydrogen is a pretty standard route, but a lot of work to be done in electrolysis to get that scale up, the costs down, because it's usually been in more niche, higher margin industries. We've also got, down the bottom, a whole bunch of technology where we've got biomass, renewable waste, etc., where we actually need renewable hydrocarbon. And pathways such as gasification into hydrogen, sometimes in combination with syngas and CO, are really important pathways. So all of those, how do we make it, are really important. We get the scale up and the applications right. Having made hydrogen, we've got to think about storing it. So we could store it as a gas, we could store it as a liquid, very low temperatures, about minus 250 degrees, and we can ship it around the world. We can also make from these resources other carriers, and people will talk about using methanol, using cyclohexane, using methane, synthetic methane, for example. All of these are potential ways of moving hydrogen around. I'm going to focus on ammonia. It's a very attractive hydrogen carrier, and it's part of an industry that's already globally positioned. It's about the second most traded chemical in the world. So we have lots of infrastructure to support ammonia shipping around the world. It's exported into many countries, I think around 150 million tonnes a year already. And then we've got the user end of it, and we'll come back to some of this. So if we want to run our fuel cell vehicle, and that's me with our fuel cell vehicle in Bell Bay at one of Neil Gross's events, If we want to run our fuel cell vehicle, we've got to get pure hydrogen. It's not always feasible to ship pure hydrogen around the world. If we use ammonia, how do we get it back? I'll talk about a technology that we've developed that allows you to do that. We want to be able to use ammonia directly where we can, because there is an energy loss, of course, in every step you do. And we're looking at mechanisms of doing that, and we'll come to that too. So I want to move through some of the technologies now that fit in that make it, move it, use it box. Let's start at demonstration and things that are near implementation. I'm not going to talk about the large-scale electrolysis factories. Electrolysis, be it alkali electrolysis or PEM electrolysis, are the mature ones, and they're the ones, as they should be, that are being put into these large factories now, produced in large factories to produce hydrogen from water, and they'll go ahead. They're at mature stage. But what are the things that are coming? What are the enabling technologies that will bring other mechanisms for hydrogen production into the supply chain? So I'll touch on a few examples of some of the early stage commercial work that we're doing, and touch on some of those three highlighted in blue as we move through the presentation. So I mentioned PEM electrolysis. The current versions of those, readily available, just need to be scaled. There are also applications, particularly in Australia, where we need energy at locations that are off-grid, remote areas. And there we'd like to make hydrogen storage and use it all in the same place. And the practicality of the processes just wasn't there. So we've worked with MPOL mainly and Main Sequence Ventures, which is CSIRO's venture capital arm. And this company, Endure, is doing just that. It's using one of our PEM fuel cells at around the 100 to 200 kilowatt scale, so not massive but significant, to commercialise an off-grid solution to replace diesel generators, perhaps at remote farming locations or places that are off the grid, if you like. It looks something like this. It gives you an option to scale by adding more boxes. You can store the hydrogen indefinitely, and that box contains both a fuel cell and electrolyser, so you can then generate the power when you need it. So that type of technology is a linker to help those off-grid diesel generators and things, if you like, to decarbonise. Next step along in electrolysis, depending where you are, solid oxide electrolysis, so a high temperature electrolysis process. You still need to use the same amount of energy to split the water, but you get a bit of a kickstart here if you apply this technology at a higher temperature in partnership with an industry where you've got some waste heat or some available heat. You can combine the electrical and the thermal heat, and therefore reduce the electrical load significantly. And in that particular example, the 32 kilowatts is about, now nothing's frozen. Oh, we're not meant to be going there. The 32 kilowatts is about the thermodynamic amount, minimum you can get. But remember, we've added heat on top of that, so you're still using more than the thermodynamic minimum. But high temperature electrolysis has a really good opportunity in partnership with thermal industries, and gives you that more hydrogen for less electricity, if you like. That partnership's developing now with a science endowment fund, with BlueScope and Ambrian, another industrial partner. So these things are coming. They're all contributions to how do we make hydrogen in different ways. I'm going to go back to sort of my roots. I guess I started a lot of my work in gasification of coals and various other fossil fuels, including gas. But that's a gateway to almost every industry that we know about. Coal gasification has been used to make Panadol and chemicals and aldehydes and all sorts of plastics and things that we might not consider coming from coal all over the world, fertilisers, etc. All of that industry infrastructure downstream of here, all of these, exist at world scale. They're commercial, they're strong, they're reliable, they're very well established. We can make, and South Africa have been making their fuels from coal or gasification and hydrogen for nearly 80 years. We can make all of those things once we've made CO and hydrogen. It's basically they've been developed in the coal industry. What our challenge is to bring that back door to a whole bunch of new front doors, if you like. So how can we bring things like biomass, municipal waste, biosolids and sewage, construction and demolition waste, etc., into an infrastructure like this, so that we then have a ready-made vehicle for transition. Those businesses don't have to go out of business. They need to just bring more of those front doors in and transition away from the fossil fuels. And then you get the advantages of scale and economy right through to things like synthetic diesel and aviation fuel, which is one of the biggest challenges. They have to have hydrocarbons, remember. We can go straight to hydrogen, and we can go straight to power. So that pathway, we want to not throw away the world refining and gas processing industry. All we've got to do is change what we put in the front end. And that's a really important thing. In our facilities, and this is just our Queensland lab, we've developed a whole lot of techniques and facilities to be able to do just that, understand the feedstock. We built these on the basis of coal, but we have in there many biomass things and many fundamental things. The science and the conversion and the chemistry is exactly the same. The molecules don't remember if they came from plastic or sewage or coal or gas. They're still hydrogen and CO molecules once they get through the gasifier. What we have to get right is the physical handling, preparation and consolidation of these things. And that's what we're trying to do in the Australian context. Elsewhere around the world, they're moving well on this. The Scandinavian countries have been doing biomass combustion and gasification for a long time. This is an example in Finland, where they've now moved, on the basis of what was a coal gasification technology to biomass and biofuels and power. Less work around the world on waste, pure municipal and solids waste, and sewage solids waste, but that's coming. So those technologies are already finding their place internationally. There's a suite that I've just gathered quickly here. Across Europe, Japan has been doing this for a long time. Swarzapumpa is one of my favourite international facilities. Multiple gasifiers, multiple front doors, as you heard me say, taking almost everything. That's plastics, timber, sewage. They have some coal because that was the platform from which they were transitioning. And they were making methanol and power. So these, and the gasifier down in the bottom left, the Premflow gasifier was originally a coal gasifier being scaled down, believe it or not, here for a biomass facility. These are big facilities. They still can plug in to the refineries and the downstream infrastructure that we've got. That's the sort of thing that I think we ought to be looking at in Australia. Another technology that we've spent quite a bit of time on, solar thermal technology. Maybe not a Tasmanian ideal place for this, but nonetheless, how do we take where we want heat? This is our facility, cartoon of our facility at Newcastle, where we have a field, about a 1 megawatt field, experimental field of mirrors. Those mirrors are tuned to follow the sun and focus the beams on a single receiver, and then that receiver stores that heat in either a molten salt, a molten metal, or hot ceramics, or what have you, and that thermal storage can be scaled to last all night. I mean, it gives you long-term scaling very easy. It scales volumetrically, so it's much cheaper than multiple battery packs because we get a cubic benefit, we get a bigger tank, you get much more incremental storage at lower cost. That also feeds into technologies that require heat. You don't necessarily have to go back to power, even though we can, and we've developed some work on supercritical CO2 turbines, etc., to do that more efficiently. But we can use that to feed into some of those gasification technologies, the endothermic technologies. We can use that heat for the solid oxide electrolyzers, etc. So in a hydrogen production, that certainly has its place, and it's a very efficient way to store large amounts of energy for a reasonably long time. Then say we've made our hydrogen, how are we going to move it? We need to sell it to Japan, Korea, places with Singapore, where they don't have renewables. So there's an industry there with great potential. I said we've chosen ammonia as a really key enabler for this, and particularly for the maritime sector. Why have we done that? Because ammonia actually carries more hydrogen per cubic metre than liquid hydrogen does. So the ammonia, which sits up here, about 130 kilograms of hydrogen per cubic metre of ammonia. So if we were to ship our hydrogen to Singapore, we'd need nearly twice as many ships if we were going to take that hydrogen as liquid hydrogen, which has got about 70 kilograms of hydrogen per cubic metre of liquid hydrogen. Now, It's nice to think we can do it with liquid hydrogen, but you're going to need twice as many ships. And you're also going to need to put more energy in. So that's one of the reasons we like ammonia. Second reason is that it's already a world-class established industry. We can talk about that forever, the various merits, but you can see there the hydrogen densities on a volumetric basis are critical for shipping. A gravimetric density is also important, but we've got to move things around. So, you said this, it's already established. We produce ammonia all over Australia. The top left, top right is the Incitec pivot plant at Brisbane, the one that Fortescue have now acquired, and we're looking at converting to green ammonia. That's about 1,000 tonne per day of hydrogen. And we, as I said, we can operate ammonia plants in cities. It's not, it's not a big scary thing. The world knows about it, we know how to handle it. As an energy storage mechanism, I've tried to indicate in the picture down the bottom, that's the fertiliser plant at Yarra in Western Australia that Yarra operate. That stores, both of those tanks are about 80,000 tonnes of ammonia each. If we were to put 10,000 tonnes of that ammonia aside as an energy battery, so the energy stored in that ammonia, just like it is in diesel, obviously, that would be around about 20 gigawatt hours of electricity. To have that much batteries, that much storage for long term and for immediate use would cost of the order of $30 to $40 billion, the batteries alone. It's just the scale and the long-term storage of chemical storage is so attractive for this industrial movement of large amounts of energy. And there are many pathways, and I won't dwell on them all. I just wanted to point out from the point of view of producing ammonia, for going to fuel cell electric vehicles, for distributed power, and for transport large locomotives and marines, there are really useful value chains based around ammonia. All those the light blue boxes are where we're working specifically on those enabling connecting technologies that will, that original messy diagram I showed you, which will connect to that spine and be able to facilitate those sort of uptakes and those utilisation pathways. I'll pick a couple of those as an example. We can't go through them all today. Then how do we use it? That's where we're moving to. Now, the first one, this is one of my favourites. We started developing this back in 2006 in what was called the Centre for Low Emissions Technology at the time, which we started in Brisbane with the state government, to improve syngas processing for coal gasification. Remember that diagram I showed you? It was purposely an old diagram. And that was, how do we get from a gasification system and a fossil fuel, how do we get the hydrogen out and leave the CO2 on the high pressure side for sequestration? So we developed this membrane to do that. And what it is a metal membrane, so non-porous metal. That's what that piece in the middle, that's the wall of a tube. So it's not a great diagram, but a wall of a tube. What happens on the outside is that the catalytic, there's a catalyst bed there that splits the ammonia into hydrogen and nitrogen. On the wall of that tube, the outside wall of that tube is a palladium catalyst, which splits the hydrogen molecule into two atoms. They dissolve into the metal, diffuse through the metal, recombine on the other side, where we've got a catalyst on the inside as well, a palladium layer. And then you end up with 100% pure hydrogen on the inside of your tubes from a cracked ammonia stream on the outside of your tube. You need to have 100% pure hydrogen for a fuel cell vehicle because the fuel cells will die in the presence of any ammonia. And that was one of the main concerns that Toyota and Hyundai had when we said, hey, we're making hydrogen from ammonia, can we put it in your vehicle? And they said, oh gee, you've got to prove that it doesn't have ammonia. None of our hydrogen comes from places that have ever seen ammonia, so we haven't had to worry about it. We were able to demonstrate that that was the case, and back in 2018, our pilot rig, which is in our Brisbane labs also, this one here, which can make about 20 kilos, 15 to 20 kilos of hydrogen a day. That's enough to refuel 4 cars. We were able to do a demonstration and refuel both the Toyota Mirai and the Hyundai Nexo off, for the first time in the world, off hydrogen derived directly from ammonia with no further purification. So that was the basis for the current project. Now, again, we're doing with Fortescue, commercialising that, and we're building a pilot plant, or they're building a pilot plant at the moment for about 200 kilograms a day, and that will define the commercial operating conditions and things for a proper scale up of that technology. I see that as one of the classic enabling technology that adds value, creates the value chain, and then can drive, for example, that ammonia to hydrogen use. It was originally set up to give you high pressure CO2 because the CO2 couldn't go through the membrane, it would stay in the high pressure, hydrogen would come out, and we would use that on a coal gasifier to do exactly the same thing. Now, you don't always have to go to the cost, and it's not a big cost, but it's a cost of producing pure hydrogen at the other end. You can actually use the ammonia itself as the hydrogen carrier for direct power generation or industrial use at the other end. The Japanese are already firing ammonia instead of coal in coal-fired boilers, so some of the burners switching coal out, putting ammonia in to displace the carbon. It's not as high energy density as coal, but it's carbon-free, and it's an important contribution to Japan's reduction in fuel cell, in emissions. Solid oxide fuel cells, high temperature fuel cells, like the high temperature electrolyzers, exactly the same technology, just running backwards, is a fuel cell. Can take ammonia directly, crack the ammonia in situ and use the hydrogen to produce power. That's an opportunity for, not yet scaled. Internal combustion engines are the obvious one. They can take ammonia with almost no modification, minor modification to the fuel system and the way you handle the exhaust. We're already applying some of that to locomotives in the mining sector. The big, slow two-stroke diesel engines for propulsion of ships will be available by 2024 from companies like MAN. These are massive engines, 50 RPM type propulsion engines. But the stationary power generation market using medium-speed diesel engines is really a simple, I think a no-brainer for this application. I'll give you a couple of examples of that. Reciprocating engines sound boring, but they're incredibly efficient and they're ubiquitous across the world. That bay of engines up on the top right is MAN engines. They're 20 megawatts each, and I think there's 8 or 10 in that particular bank. So you've got 200 megawatts there of almost infinitely variable available power. That's running on oil. They can run as efficiently on ammonia as they can on fuel, with some modifications to their fuel injection systems. So very high efficiency. The engines are well understood. They're reliable. They operate for up to 50 years. They have efficiencies comparable with fuel cells, and they're very tolerant of impurities in the fuel, so they really can accept quite tough treatment. Many of you will have seen around in many applications the smaller types of diesel-based generators, and they're the ones we're looking at now of how do we start to replace those with ammonia-based things. Now, there are some peculiarities of ammonia combustion around the ignition, around the low flame temperature and so forth, and that's why the work that we've been doing in the research space is to try and make sure we can address those questions when they're asked. And for that work, we've done quite a bit of work on flame propagation. We've got 2 engines in our lab at Newcastle, a single-cylinder sort of workhorse engine that gives us room to play with it in the cylinder, and a more commercial 3-cylinder engine, which we've got variations of injection port or direct injection. We've got a turbine, we won't go into that. You do have to manage NOx differently with an ammonia turbine. But that gives us the experience to work with the engine manufacturers on how do we develop appropriate systems, right down to the ignition of ammonia. This is a high pressure combustion spray chamber, and in this particular picture here, we can see here the very point of ignition, and this is ammonia spray at 200 bar pressure. A couple of milliseconds later, that flame front's beginning, and there we have the flame front of the ammonia spray. So we can look at what will happen in the engine. I'll get to your question later.
Sorry interrupting you, but what about counting the exhaust gases? What about the NOx in the exhaust gas? Because by definition there will be a lot of NOx in the exhaust. Yeah, everyone thinks that.
The flame temperature is quite low. This is not like a high temperature flame, so the NOx production is not as high as you think. And it is readily managed at the exhaust. The bigger issue is actually ammonia slip, that we don't get full combustion in the chamber and you actually get ammonia slipping through. And that we can also manage. Believe it or not, we use ammonia, that's why the power stations were so happy to use it. We use ammonia to reduce NOx in power plant. It's actually injected after the flame front to reduce the NOx. So we can manage the NOx. Yes, it can be formed, and that's one of the reasons we're looking at the rate of combustion in the engine. Through timed injection, you can manage the flame temperature, and that's the way to manage for NOx. And that's exactly where we're going. With appropriate injectors, programmable injectors, particularly in the slow engines, you get multiple shots per compression stroke in some cases. So that is, that's how we manage some of that and get the appropriate fuel mixing. And we've developed, and this is the sort of program that we're trying to work towards. We've done, I think, the proof of concept. We now are working, and this is what I was in Singapore this week for, to start to get some demonstrations of these things on the ground in real practical systems. Straight away we can go to a 95% diesel replacement with ammonia. You still need some help with ignition, as I said, difficult to ignite, so there's a couple of percent of diesel in there to do that. We can easily envisage moving that forward when we're optimising the process by simple things like biofuel. We only need 5%. Or we can go to full ammonia, with a bit of a tweak. I would suggest using our ammonia cracker even to give you a little bit of hydrogen in the fuel. But that's next step. The key is how do we get this into industrial demonstrations so that we can start to get the industry confident and have these things implemented in businesses. It's not, if that was sitting next to a bunch of diesel engines, you would hardly know the difference, but the operators have to come to terms with a different fuel ecosystem to do that. Now let's look at how these are being implemented across the various industries. Japan has had a project going, I've been involved with it since 2010, and that's a coal to hydrogen process. Now they're looking at liquid hydrogen transport to Japan, and we need all pathways. So that's now, the pilot plant project is now done, and they're at a commercial decision stage about whether to scale that up to a large coal gasification facility with CO2 storage for liquid hydrogen to Japan. So these industrial ecosystems are being developed. That value chain is very much like the one I showed earlier, and that's bread and butter now for Japan. Groups like Rolls-Royce and many others are looking at these ecosystems, all of which require renewable energy, and that can either be locally or imported in the form of hydrogen, and in all of these, hydrogen is at the centre of those ecosystems, whether it be for power, for fuels, or for chemical feedstocks. Remember, we still need to make plastics and all of those things right front and centre in some of these major players. And the reason I was in Singapore until this Friday was to talk about implementing one of these diesel engines, perhaps in a port situation. Singapore has the world's largest, busiest port. They have to decarbonise that entire port, and they're going to move the port in the next 2 years to a new location. Big decisions have to be made about infrastructure and about how do they decarbonise that port. And this, is, to me, is the ideal sort of opportunity to start to demonstrate some of these new technologies. We've got an arrangement with Singapore, which we helped set up a few years ago, between Singapore and Australia. We've got $30 billion government money from both governments, so not 30 each, but 30 total. And we're looking to twin that project with something in Australia, and I hope Tasmania, because these implementations are really essential to get the industries comfortable to invest and move forward. Because what we have to do is actually create a whole new industry that will ultimately be the scale of the global oil and gas and coal industry. We've got an opportunity to be an exporter in that. Obviously, one day our coal exports will decline. We've got a great opportunity to replace that with renewable energy exports in a number of forms. It's a really broad area. It's no longer just the energy sector. It's manufacturing, transport, agriculture, all of these things coming together. And ammonia is the basis for fertilisers, for goodness sake. They know how to handle it. So we need to bring those sectors together and demonstrate these technologies where we have experts, but they're not talking to the other experts. And that's where the partnerships and collaboration are absolutely essential. Or we'll do the research forever and we won't see that deployment, or the risks will stay high and we'll be stranded. So that's, I think it's an optimistic, but it's a challenging space. And the scale is way beyond what people tend to traditionally associated with biomass and things, which are largely either enterprise broad or sort of by this comparison, basically cottage industries. We've got to change that mindset. The molecules don't remember where they come from, but they still need to go into really big plants to make the fuels and the energy we need. So thank you. Sorry I went a bit over.
You'd be happy to take some questions?
Absolutely. There's lots more.
I think we've just had a lecture of a sign of things to come, ladies and gentlemen. think it's an exciting future. Questions?
What strike you as the major impediments to what you are hoping will occur?
Read that question. Oh, right, the major impediment is getting started. It's having industry start with some of the small steps. There seems to be a mindset that, we will go and we'll start making one part, and we make a tacit assumption that the renewable energy will be available and it'll be free. That's not true. We need to look from our end as a potential exporter at the impact not just of my technology, be it making methanol, ammonia or hydrogen, but how are we going to ensure that we can actually put the electricity in. We can't take all the electricity from the existing grid. It doesn't exist. So the capacity must grow up to support these new projects. The demonstration has to be at industrial scale of relevance. So in our case, we want to start demonstrating these with ordinary ammonia. Obviously, there'll be emissions where the ammonia is made. It'll still be zero emissions at the point of use, and accept that we're going to have to transition. But not doing these demonstrations because the whole value chain's in place, I think is the biggest impediment at the moment. People are looking at their own spot. We're not talking between sectors. Many of the solutions exist, but they're just not connecting.
Just one quick follow-on. So what strikes you as the best mechanism or structure or whatever for having those intersector conversations happening?
4 years ago, I thought it was a bilateral relationship like we were striking with Singapore, where and the relationships we have with Japan. I think they've been very good at activating the market pull, if you like. They've been less good, I think, at getting the appropriate enthusiasm in Australia. I'm not sure why. I guess COVID had a bit to do with it because we didn't get around. But the mechanism where, say researchers, where researchers sit down and shut up and listen and understand what the barriers are. They're not always a new technology. I've got a new whiz-bang technology and you need it. The issues are multifaceted business and ecosystem issues. We're only going to understand those by working and talking with the actual potential users. And researchers tend to have not been doing that well, and that's what I'd like to see as change, because once the industry knows what it needs, and we all don't know what we don't know, we can start to even direct the more blue sky research in relevant directions and get the guidance from industry to make that happen. But we don't listen enough.
All these technologies require more electricity.
Yeah.
We're running short of electricity in Australia already. Do you see any hope of this transition without nuclear power?
Oh, that's a really interesting question, and that would only have to be a personal and hypothetical response, because at the moment there is no option for nuclear power in Australia. But you're right, much of this needs, as I said, massive scale of carbon-free power. Some of them don't. The gasification pathways, as I said, don't, and that's why we need to maximise them too. But you're right, we need a strong source of reliable, 24/7 power, be that variable renewables with storage, or be it a means of carbon-free baseload. There were the Japanese projects using coal-based gasification with sequestration. With CO2 sequestration, you could do some of that. But you're right, I mean, carbon-free options of large-scale power are limited, and nuclear is a good option, but it's not on the table. So it's not something that we're actively pursuing, but it's obviously factored in the life cycle analyses and economic analyses. And other countries are doing that.
Following the question, in your presentation you said that to make 1 kg of hydrogen it takes 32 kilowatts energy. How much energy we get from 1 kg of hydrogen?
Oh gosh, I should know that number.
Roughly I give you.
Hydrogen, about 18 megajoules per kilogram, I think. Now I've got it in my...
Yeah,
I've got it. Hang on.
The same question, I'm sort of concerned that we have to put more energy to produce the hydrogen than we do, right?
You won't put more, but there is no free lunch. That's exactly. And here's an example. And I thought I wanted to ask why not go liquid hydrogen versus ammonia? The same thing. The electrolysis pathway you need to produce it's about 70%, 50 to 60 to 70% efficient at the moment. It's the same as a battery. You put in 100 kilowatts, you'll only get out 70. The same with this. You've got to put in more power than you get. That's why the best strategy is use what electricity you produce when you produce it. But in the case of renewables, where you have high and then low, you need to store it. So you pay a penalty for that. Even in pumped hydro, you pay a penalty for that. So you've got to pay the piper. Every single step of the way, conversion, you've got to pay in lost energy and cost, and that's why we're looking. If we were to ship liquid hydrogen versus ammonia, the losses are greater in liquid hydrogen than they are ammonia. Exactly the same reason. Every conversion step costs, and there is no free lunch.
So overall efficiency, what would you say?
Overall efficiency.
From A to B.
Well, it depends where you are, and it depends what you're using it for. If we could go from hydrogen to ammonia to direct-fired diesel engine, our efficiency losses are significantly less than if we go hydrogen to ammonia to hydrogen to a fuel cell vehicle. So it depends on your application, the distances travelled, etc. But yeah, you're always going to have losses. So here, this pathway, the bottom pathway, is far less losses. Top pathway with liquefaction, more losses. So it depends on what you do. You get a different A to B.
Excuse me. Excuse me. What sort of kilometre range is your cars doing?
On the
tank for?
The hydrogen car or the electric car?
Hydrogen car.
The hydrogen, again, I know about the Mirai because we've driven the Mirai. You get about 600 kilometres to a tank from that car on 5 kilograms of hydrogen. And of course you can refuel it quickly if you've got a refueling station. A battery car, you can get anything from 300 to 700 kilometres per charge, depending on the size of the battery, of course. But most of the hydrogen cars have around a 5 kilo tank at 700 bar. A bigger truck would have a bigger tank, maybe 50 kilos of hydrogen, only a 300 bar. They probably go 1,500 kilometres on 50 kilograms. Big truck running on a battery, 30-tonne truck, would probably need a 12-tonne battery. It would have nowhere near 1,500 kilometres, and it would take a long time to recharge. So about 500-600k for a Mirai, let's say. Depends how many hills.
Sorry. I'm just trying to give you some exercise.
Yeah, so it struck me that maybe something like 2% of the world's energy currently gets used to make ammonia or these sorts of products. That's potential storage. You know, they talk about we need more storage in the system as a whole for being able to transfer to non-dispatchable renewables. And that seems to me like a potential source of storage because you can make the ammonia more when there's the spare energy, although some problems with capacity to turn the generation up and down. But it doesn't seem like we have the systems in place as a society to make that sort of thing happen. So for instance, when the price of the feeder stock for ammonia goes up, like the natural gas and most of it's made from at the moment goes up, people turn the ammonia plants off because the price of their product hasn't gone up yet, and then we get these massive swings in price that go on. It seems like there needs to be something other than the market that makes these things happen because the market's not responding well to these things.
Yeah, partly because of the availability. We don't have the plethora of, the question over here was about that, we don't have the plethora of renewable energy which is stored to give you that 24/7 operation. Now, theoretically, by having a large amount of renewable energy available, we should be able to avoid or reduce the big oscillations, for example, in fossil fuel markets. if it's local and we're processing it locally. We'd had this discussion in Singapore because they're exposed to this more than we are. But technically you could break some of that nexus to the market by integrating storage, but you've still got to have a large capacity, as you say, so you can store enough to operate during the day or have enough to operate during the day and a buffer to store. And if that's integrated, then your prices should be relatively flat. But yeah, the market we have on the grid at the moment isn't flat, and we have secure supply for coal and gas in Australia, but the market's not. But yeah, you're right. It's going to rely on a huge amount of generation and storage. Chemical storage has an advantage in that you can store a lot in a small place, and you can get it all back when you need it. If it's an hour away or 6 months away, you don't lose anything. The battery will be flat in 6 months, but you know those mechanisms of storage and transport will help smooth that out.
They've taken the storage out. We used to have more storage, but now they've gone to this just-in-time systems, which are much more volatile.
Yeah, but we don't have any storage, basically. The only storage we've got now are at household level or a couple of big batteries, which are 10 minutes. They're about taking out variations in the grid. They're not about putting energy away for later. At least with an export market, we should be careful, because with gas, prices did go up as soon as the export market opened. It will be exposed to the international market, and therefore we may end up generating an economic conundrum the same way, like opening our electricity grid to the world. Will our electricity prices follow that demand? I don't know, that's not my space. but we haven't got enough generation. There's only 17%, if that, of renewables in our national grid now. So there's a long way to go before we've got capacity. And I'm sure the Tasmanian experience is that great, it's all renewable energy, but you're using it, of course, and any new industry is going to need to have new capacity. Otherwise, there isn't any for storage. Yeah.
Yes, as David has said, I'll sometimes refer to it as having a second bite of the cherry. This is a very particular question. About a quarter of the way through your talk, it was just a single sentence aside about, instead of parking CO2, using CO2. Is there some way on the horizon of using it as a resource rather than an irritant to be got rid of?
Yes, and we do use CO2 now in every one of those processes that make methanol and things, the CO2 that's generated.
Apart from plants. Apart from plants.
Apart from
plants.
Plants. Yeah, well, we're using it now in the commodities that we produce, but we can't use it all. I mean, almost by definition, CO2 is rejected out of making hydrocarbons with a lower carbon-hydrogen ratio, which is what we need to do. And CO2 is the lowest energy level. So anything you do with CO2, you've got to put energy back in to make it into something else. And that's what people are looking at, using CO2 either captured from the process or even captured from the air, and don't get me started, but captured from the air and put in with hydrogen, so we can make so-called green methanol. And that relies on so-called green carbon. And that could be defined as carbon from biomass, so you convert your biomass to CO and hydrogen and then make aviation fuel. That's got green carbon in it. But your straight biomass has too much carbon, so we either reject CO2 or, more smartly I think, add extra hydrogen. That way that the CO2 can be used. Now it'll still end up in the atmosphere in those scenarios, but at least it's got two goes at the cherry. But the utilisation amount of scale, if we were to take all the CO2 that's emitted from the fossil fuels, now it's too much. The biggest use at the moment is enhanced oil recovery groups in the US and others, using CO2 to get more oil, push the oil out. Those empty reservoirs have huge potential for sequestration at reasonable cost. So what we can't use, and one would argue should we be using it, there is sequestration possibilities available while we transition, but the scale of the production is way beyond any current industries for utilisation. Soft drink and beer use some, but it's not enough.
I'm working on it.
We need more there.
Any other questions?
So one of the things that concerns me is feedstocks that are reliant on land use, because at the moment we're at this critical situation where we've got biodiversity depletion and risks of food security with availability of ag land. So I just see a bit of a concern. We've gone down the track before with using biofuels and sewage sludge and things that should closed cycle economy. They should really be going back onto the land, not into the fuel cycle, to maintain that sustainability. That's my concern about some of these fuel stocks. I mean, we've gone down that path in North America and in Europe. They've realised their mistake, and now they've got an industry dependent on it, and they can't change their policy, even though they know they've gone down the wrong track.
Yeah.
So there's a chance to not do that again with this.
There's a big chance because we need lots of land, let's say, for the low density renewables like solar and wind and that. They need a lot of land, which would be hopefully desert land, but it could be farming land. It depends on their commercial locations for access to factories if they're going to convert the stuff to ammonia or something. So again, that's always an issue. The old food versus fuel issue is a real one, and it's the same now. Best use of land should, and I did make a quick mention of best use of feedstocks. If we've got so-called green carbon, should we be spraying that across everything or reserving that for industries that have no choice, and working harder on some of the other pathways like ammonia, hydrogen and so forth, where fewer industries can use that, more industries can use that, they have a choice. So it's about getting the big picture right rather than necessarily optimising on a particular project or location. We have to optimise at a higher level, or we're doing our grandchildren a disservice, because we'll end up using up the green carbon very quickly when that could have... As I said, the whole world's oil and gas industry is producing fuel for cars and trucks and aeroplanes. And if we have to have hydrocarbons for all of them and shipping, then it's got to have hydrocarbons. And we know that some of them we can shift and not have hydrocarbons. So they have a choice. I don't think aeroplanes do. Big aeroplanes.
I'll send you a picture.
Yes, so from your presentation, I get that we need power and water to make a hydrogen. Have we got enough of those two in Australia to make the hydrogen on commercial scale like we intend to do?
Have we got enough water?
And power.
We haven't got enough power. We'd obviously have to cover a lot more of the land with, let's say, PV. Now, there was a study done last year called Net Zero Australia, done by Princeton and UQ and others, University of Melbourne as well, and they looked at what would it take to be a Net Zero Australia with the sort of industries that we're talking about, and the area of land. People often put this little picture up that if there's only that much sunlight. If you actually factor it in with the efficiencies and things, I think the number was 7 Tasmanias. So across Australia we would need 7 Tasmanias of solar PV field in area.
I agree with that, but so it will take quite a substantial amount of money to get to this stage, to generate enough power. Could be done, but what's about water? Like every summer, or maybe not every summer, but quite often we've got a water restriction, Sydney, Hobart, Melbourne, whatever. So have we got enough water to generate that much hydrogen?
Comes down to cost. You can desalinate at a cost.
Very expensive.
Yeah, of course. It comes down to cost. Many places do have enough water. You're not going to do it everywhere. And that's, do your 7 Tasmanias, go somewhere where there's water, or is this, what wins, the solar availability or the water availability or the access? So that has to be worked out appropriately. But it's not so much water when you think about the quantities of water involved, but it's a significant amount of water. And it has to be the appropriate purity at the moment, although there are people working on direct seawater electrolysis as well, and that would change the game significantly.
Great. Thank you.
The discussion at the moment about exporting hydrogen or ammonia, whatever, from Tasmania, from what you've said, that's sort of losing at least 30% of the energy just in the processing. Would we be far better to think about processing rare earths or lithium and other elements directly in Tasmania rather than going via the export of hydrogen route?
Yeah, I think in lots of industries, if we're currently shipping any of these metals overseas, having them processed and bringing them back, and we're shipping the energy overseas to get that done as well, it's worth rethinking about shouldn't we be adding value here. The iron ore industry start asking exactly the same question. We're currently producing iron ore and sending it across to China, Japan, etc., where they've got to then reduce that iron ore and produce the steel. Should we be using the local solar energy, for example, to pre-reduce that iron ore here? So should we be doing more value add in Australia using the energy rather than shipping the iron ore and the energy and then buying back the product? I agree, and the companies are looking closely at how do they integrate renewables into either their blast furnace operation or their ore beneficiation or whatever it might be, to see if it is worthwhile. Now there's some catches there because you've got to heat material twice, once in Australia and once in China, so there's a cost in that, but is the net result better? It's better economically, you get more money here, but is the net emissions result better? Then you've got to look at that life cycle. But that's exactly where the aluminium and steel and iron industries are looking. Should we be adding value here? And the rare metals the same. I mean, do we send a concentrate or do we use the renewable energy here to do it? And I think some of them at least are very serious about adding more value here if they can work with their client and have a satisfactory product. But it comes down to cost price.
I think we're coming up to the last few questions.
David, coming back to Russell's first question about nuclear, it's not on the table, but every time a politician's asked about it, he says, or they say, it's too expensive because solar's free. The issue of generation of energy, getting to the consumer is the big issue. Do you know of anybody that's looking at the economics of each of these big pathways, including nuclear, that says if we produce it, how much does it cost to get it to the consumer? Because all these are just different ways of, feeding a consumer.
You mean with electricity?
Yeah, with electricity. Well, electricity is the whole issue, isn't it? We're talking about energy. And these are all different energy pathways. We're talking about carbon-free. Well, carbon-free energy, nuclear is. It's off the table, but politically, Germany's just switched all theirs back on because it's hurting everybody's pockets. So the pain that the community feels generates decision-making. So do you think there's potential to get someone to look at each of these pathways and really paint the picture of what impact it's going to have on consumers, industry and, I guess, just private consumers?
Yeah, I guess short of a change in policy, you can do Martin Thomas led a group 10 years ago looking at Australia's nuclear opportunities, I guess. Now technologies have moved a little bit in that time. One of the challenges is the time it would take Australia to get going in this industry, and some estimate 20 years before we've got the skills and the capabilities and the plants in place. Is that worth embarking on? I don't know. The politicians say no. But no, that's not something that we've looked at in detail, but it probably should be thought about because internationally those reactors are forming part of the system. Now, one might argue they don't have the, let's say, inverted commas, luxury of a large amount of solar and wind that we may have, but we can factor that into that equation. Now, I'm not sure if the net zero study that I referred to included a scenario with nuclear or not, but I can find out. It would have been the right sort of study, I think, to factor that in. They would have been they did exactly the same study for the US, different market, but I'll check that out because in the US that would have had nuclear in the mix and we'd be able to have a look at some of those Sankey diagrams and how that worked. I don't know offhand whether the Australian study did an option like that. But that would be the cheapest way to do it because the framework's all there, and if we've got the data, we can plug it. Neil, got to have a question from there.
Sorry, Dave. Do you think the Inflation Reduction Act in America and the amount of government money in America going towards hydrogen generation will draw research away from places like Australia over to the United States?
Draw research away. Possibly not. I mean, it could open opportunities for us to partner with them, and very rarely do you get money coming through these systems between countries, but you often get a platform where you can collaborate. So it may give us some opportunities to share facilities. I'll take for an example the work we're doing on the supercritical CO2 turbines. We originally in Australia embarked on our own program looking at that. A very, very attractive pathway for a closed loop of supercritical CO2, very small turbine, very efficient. It was crazy for us to be making our own when in the US there was a $200 million program with GE and others doing that. What they didn't have was the access to some of the, in our case, the solar thermal units to be able to test that. So we got the benefit of access to their turbine, and they were able to use some test work with using some of our platforms on solar thermal. So there's a way to leverage those things. I don't think it would draw research away per se, because the way the American system works is it focuses very much on America, but the technologies have value elsewhere. Now, what it is doing perhaps is attracting industry investment, which will go into, they get the leverage and the subsidy, if you like, into industrial projects. I think it could facilitate better collaboration in the research space, optimistically, rather than draw it away. I think it actually gives us a platform to collaborate better, leverage our own funds.